Hello guys, in this video I'm going to show you how to implement tree data structure. Let's see, create a node class constructor to accept an argument that assign data. Initialize an empty array for storing children. But first let's see what is actually true, how trees look like. Tree data structure. It's better to have visualizations. As you can see, here is a tree. This tree is composed of nodes with there's a root node, which is the node that has no other node pointing to it, right? So there's nothing pointing to yeah, but it has 5 children. We call it the children node. These are all children of root node, right? And so it's same here. We have 2 is the children of 9, 12 have 3 children, 8 had no children, and so on. So this tree has 3 levels. Here the first level, the second level, and third level. So a tree typically has data and children. So the root node has data of 2, and children are actually a list of pointers that keep the references to each children. So that's pretty much it about tree. Let's implement it. Now we're gonna implement the node class. The node class represents a node here. Okay? As I said, a node may have data. This is data. We're gonna take the data from argument, and also we keep check a list of children. It's a list. We initialize it as an empty array, which has no children. We should accept, alright, initialize empty array. So the node class should have method adds and remove. For add method, we take in the data. How to add a node to a tree. No, not a tree, sorry. We add a node to the children list of current node. This method actually add a child to the current node. So we create a new node, go to new node with data of data, and simply push the new node to the children of current node. This children push new node. It is not very difficult to understand, I think. So for remove, we will remove by data. And what actually this method do? Actually, it will remove a child from the children list, the one that has the data equal to data argument here, right? So we need to find in the list, children list, the node that has data equal to data argument. So let's say we want to find it by index, so we can use index to remove from the list. Con index equal to this the children, we want to find by index, right? Index with node dot data, we want to find the one equal to data. Okay, so if index greater than -1, index is equal to -1 if there's no element found, matching found. So we want to make sure that we only remove element if we found it in the list. So with the children, we want to supply. The supply method will remove by index, right? And we also need to specify the number of elements we want to delete, which is 1 in this case. So let's test it. There are 4 passing tests, right? 4 passing tests. Alright. So all not related tests are working now. So now we'll move on to tree class. The tree constructors will initialize root property to know. So constructor, we want to initialize the root property equal to no. What else? Implement traverse breadth first and traverse depth first. What is depth first and what is breadth first? Let's see. Breadth first search is pretty common way. There are 2 common ways of traversing the tree, which is breadth first search and depth first search. Let's see. For breadth first, it means we will traverse layer by layer, right? So the order of traversing the tree, this tree is 2, that 3 level, right? As I said earlier, 1 level, 2 level, 3 level, and we travel by the level. Start with the root node, which is 2. We go to level 2, the second level, which was 9, 12, 8, 99, 10. Then we're done with level 2. Go to level 3, 1, 2, 7, and so on. So that's the breadth first search. So let's implement it. To traverse in breadth first fashion, we need to use a queue. So let's a queue, but definitely we don't want to traverse if the tree is empty. So if this row is no, we want to simply return we initialize a queue, push root to the queue, and as long as queue is not empty, which is the length is greater than 0, we take the current node, not the node at the head of the queue, not equal to queue. We want to for queue we have two operations, enqueue and dequeue. To enqueue we're going to use push, and dequeue we're going to use shift function. These are built-in functions of JavaScript array. So we want to dequeue, which is shift, right? Shift. We take a node, right? We check all of its children, child of node children. Then we push the children to the queue for later processing. Queue dot push child, and for every node that is pop out from the queue, we want to, of course, run the callback. We want to callback and give it the node itself. So that's it. Hopefully it will work. Alright, we have one failed test, which is the Javas DF, because we haven't implemented it yet, so let's do it now. For Javas DF, taking a callback, we want to run the callback for every node. So same as above, if it's an empty tree, we're going to return away. Would create for depth of search. Remember, breadth of search we use a queue, for depth of search we use a stack. Con stack equal to this dot root. Actually, it is same as initialize a empty array and push. We simply push into the queue. So by doing this way, it's a little bit cleaner. So as long as our stack, there's something in stack, we want to run in the loop. Otherwise, we exit the loop. Cons not equal to, we take out the one in stack. For stack, we use push and pop. Okay. Push what? Push. No, we want to pop it down first for pop, and we want to run a callback, passing the node, and want to check for every child of the node children, for every child. For every child, we want to push it to the stack. Okay, let's see how it works. It fails, so ADBC is the order that is the result, but only one is A, B, C, D, E, right? So the program might be, because the order of, how to say, as you can it's a matter of ordering. So as you can imagine, A is the root node, right? Then B, C, no, B, let's see the example. A and B, C, okay, B, D, A, the child of A is the root node, B, D, let's visualize it now. A is root node. Now here we have B and D is the child node. And for the third level, we have D and C is the child of B. So the expected result is A, B, C. You can see it go depth first, A, B, C, and D. But the result, our result is A, D, B, C. It's just because we traverse the D first, but not the B. So the problem is here. So to solve it, one quick way to fix it is to reverse the children list, right? So let's see. Awesome. Thank you for watching. See you in the next video.